Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, what we will do is we will be fitting a slightly different version of our simple linear regression model. The change that we are introducing is centering the predictor prior to estimating the slope and the y-intercept. Then we will compare the estimators of our old model with the ones for the new centered model. Okay, and finally, as a bonus, we will carry out a hypothesis test for this new centered model. Make sense? Okay. Let's begin. As usual, it would be beneficial to start our discussion with an example. Okay, so consider the following data. One, 2.1, 2, 3.1, 3, 3, 4, 3.8, and 5, 4.3. So, let me remind you, first we're going to be fitting our old model. The old model looks like this. We have yi, where, as you know, that guy represents our response variable, and then we have a beta 0 plus beta 1 xi, that represents the value of the predictor variable for the ith observation, and we have an epsilon I, the random fluctuation for that particular observation. And in this case, well, I goes from 1 to 5. We have 5 observations. Okay, and as usual, we have our assumptions about that random fluctuation, that epsilon. We are going to be assuming that those random fluctuations have a normal distribution with mean 0 and unknown variance sigma square. And of course, we are assuming that those epsilons are independent. Okay? Okay. So, as we said, right, our first goal is finding estimators for beta 0 and beta 1. the y-intercept and the slope parameters. Okay. So first goal, estimating beta 0 and beta 1. At this point, right, we have a few choices to find these estimates. We could apply the formulas that we have derived together, remember, using the normal equations. Another option would be using linear algebra to find these least squares estimates. Another one would be just using R. Okay, so let's do that. Let's find them using R. Let's find the estimators or estimates, because in this case we have numbers, right? The estimates of beta 0 and beta 1. And the difference between estimator and estimate is subtle. We are going to say that we have an estimator when we have a formula, right? Something given in terms of these generic observations, the yi's, and an estimate when we actually find the numerical value for a particular example. Okay, just, you know, a note on the jargon, the technical jargon. Okay, so we said that we're going to be using R. Let's launch R. Okay, let's see, we have these, the first coordinates represent the x, the predictor variable. So in this case, x is going to be just 1, 2, 3, 4, and 5. So let me use this built-in command. We're going to create a sequence that has as a starting point 1, as ending point 5, and the difference between each of those elements in our sequence will be 1. So let's check. Yeah, that's exactly what we want. And I did that because I'm a lazy guy. We could have done this in a different way, using that C function, the concatenate function, and it would have been C brackets 1, 2, 3, 4, 5, then brackets, and it would have been the same thing. Okay, so here we go. Next one, the response 2.1, 3.1, 3, 3.8, and 4.3. Okay, now as we already know, and if we don't have that in mind, let me remind you, when we are doing a linear regression, a very important step is making a scatter plot, seeing whether or not it makes sense to assume that we have this kind of linear behavior, right? If that model makes sense. So we know that to make a scatter plot in R, all we have to do is use that built-in function plot, then place the vector that contains the values that go on the horizontal axis, and then the values on the vertical axis. I'm going to be using this additional parameter PCH because I want to have solid circles. I want those solid circles to be blue. Okay, and there we are. So based on this scattered plot, it seems like a reasonable assumption that we have a linear model. Okay, good. Now we said that we would like to find the estimates for these guys, right? The true y-intercept, the true beta 1, the true slope. Okay, so to do that we're going to be using that built-in function called LM that stands for linear model. But I would like to save the objects contained in that linear model in an R object that I'm going to be naming old.mod, as in old model. Okay, so first we know that the syntax is first you place the response, then tilde, and then the predictor variable. Okay, if we want to see the values of the coefficients for that old model, all we have to do is use that built-in function and the name of the model we are referring to. So in this case, beta hat 0 happens to be 1.73 and beta hat 1 happens to be 0.51. Okay, so let me write that down. Oops. So using R, we have that the estimate for this guy, and remember that the notation that we're going to be using to refer to estimators or estimates will be that hat notation. So 1.73 for this guy, and for beta 1 the estimate this particular case, given that the sample of ours .51. So easy so far. Okay, now just for fun, let's add to that scatter plot of ours, let's add the least squares regression line that we found. Okay, so let me plot this guy again, right? So it must be here. There we are. But now what we're going to be doing is adding to that existing scatter plot the least squares regression line And remember that this guy, AB line, it's a built-in function that is going to allow you to draw a line to an existing plot, a scatter plot in this case. But the syntax of this guy, of this AB line function, is you need first the A parameter, which represents the intercept, and the B parameter, which represents the slope. And that's exactly what we have here when we use coef and then the name of our model. Okay, so in this case I want a red line, and since I want a dashed red line, I'm going to be using this parameter LTY equals 2 is telling R that we want a dashed line. There. Okay, looks nice. Okay. Let's continue our journey. Remember that at the beginning I said that we were going to be studying a different version of a simple linear regression model. So you have seen that model before. That's the old flavor of our simple linear regression model. But we said that what we're going to be doing is for this new model, this centered model, is we are going to be modifying our predictor variables slightly. We are going to see what is the effect of centering our predictor. Okay, so let's be more specific. Let me write down the new model. So the new model is going to be similar to the old one. The y's are the same, right? Those are the responses that we are observing. To make a distinction between these guys, let me use a superscript star. I'm going to have a different slope here, potentially. And the difference between that old model and this new model will be this. Oops, not what I wanted. I want a bar here. Oh no, not what I want. Sorry. This is the one I want. Okay. And well, you know, potentially these guys, these errors when I make that change are also different. So anyway, can you see that this is what we mean by centering our predictor? Okay, we are centering with respect to the sample mean. Okay, so let's see what's the effect of this change. Let's, just like before, let's find the estimates of beta 0 star, the new y-intercept for this new model, and of beta 1 had star, the estimate for the new slope. Okay, let me say that we're going to be finding those estimates. Just like before, what we're going to be doing here next is using R to find those estimates. And you'll see it's going to be easy to implement that change. So first, we already have X, right? We need the sample mean. Well, there's a built-in function in R called mean. And it makes sense, right? Oh, 1 plus 2 plus 3 plus 4 plus 5, that's 15, divided by 5, that's 3. Okay. So now let's create a new object called new.x, which is going to be the centered version of the predictor variable. So it's going to be x, the old x, minus mean of x. Let's see what it looks like. Makes sense? 1 minus 3 minus 2, and same goes for the remaining 4 components of x, the old predictor variable. Okay? Just like before, we're going to be using the lm function in R to fit our new model. Okay, here we go. Now let me create a new mod, as in new model. We know that the syntax of lm is first you need the response, then the predictor variable. Just like before, if we want to see the coefficients that define our new model, we do that. Oh, okay. Let's write that down. Okay. Let me copy and paste this, and we are going to be making a few changes. So now this guy, instead of being just a plain beta hat, is one with a star, meaning for the new model. Now this guy, instead of being 1.73, is 3.26. So it changed. This guy, star, and this guy, oh, that happens to be the same. Okay, nice. So the estimates for the slope, those match. However, the estimates of the y-intercept don't. So now we wonder, maybe predicted values, the y-hats, will differ as well. And again, let me just, if you haven't seen that notation, let me use, let's just say that notation. When we use a hat for the y's, these are predicted values, meaning they come from our model. Predicted value of yi. Okay. So anyway, if we wanted to make that comparison here, we could do it like this, and then we would see what we just saw here, that the slopes match, but the y-intercepts don't. Okay, so but what we wanted to investigate was if the predictions differ, the y-hats. Okay, so how about we start with a single value? How about x bar? That looks convenient. Let me tell you why. Because x bar, if you plug in to come up with a prediction, all we have to do is plug in, right? So if I plug in the new model for the xi, I plug in x bar minus x bar, gone, and then the only one that remains is going to be the beta hat star, right? So let me just say that in the case of the new model, if you want to find a predicted value, it looks like this, 3.26 plus 0.51 times this, right? Because we don't get to observe the errors. So this is the equation that we have. Just approximate these guys, and then, well, these are random fluctuations, and we don't get to see those, right? What we're doing is minimizing those. And in this case, let me do something similar for this guy. For the old model, this guy is going to be 1.73. This guy is just going to be xi, if you want to get predictions using the old model. But we were saying if we used x bar here, then for this one is going to be easy. The predicted value for x bar will be just, this is going to be 0, so the predicted value for x bar is going to be 3.26, and then for this one it would be, well, 1.73 plus 0.51 times x bar. Okay, so we could do it by hand, like this, 1.73 plus 0.51 times the mean of x, and that's 3.26. And that's the old one, and we know that for the new one it's going to be 3.26, so predictions match. Interesting. So there's a way of getting all these predicted values not by hand, but all of them at the same time. Okay, because we want to see whether or not this is just a coincidence that for x bar we have something like that, that the predicted value for the old and the new models match. Okay, so here let's type names and then our old model. See, so we have coefficients. We have seen these before, right? We used this to to add to our scatter plot the least squares regression line. Okay, now let's talk about these guys, fitted values. Okay, let's type old mod $ fitted values. This is how you could get all the predicted values. In this case, when x equals 1, that's what you're going to get. When x equals 2, 3, 4, and 5. Make sense? Okay. Let's do the same for the new model. As you can imagine, the only thing that we have to change here is the name of the object. And as you can see, those fitted values match. Okay, let's recap. So first, we fitted our old regression model. Then we obtained the estimates for a new regression model. Okay, the new model is one where we used centered values of the predictor. That is, the original x value minus its mean. So what we observed was that the estimate of the slope parameter is the same for both models. The same can be said about predicted values. Both models yield the same predictions. Okay? On the other hand, the y-intercept differs between the new and old model. Okay? So the y-intercept for the old model and for the new model, those are not the same. Okay? Another interesting thing. Let me show you something. We saw that the mean of x equals 3. And we saw that the predicted value, the corresponding y for 3, which happens to be the mean of x, is 3.26. Just out of curiosity, let's find the mean of y. The mean of y happens to be 3.26, the mean of the response variable. So what we're seeing here is another interesting feature of the least squares regression line. The least squares regression line passes through the point x bar, comma, y bar. And you know, these observations hold in general. Okay, so we said that another goal of ours would be to using these ideas to carry out a hypothesis test, right? Hypothesis test for the slope parameter, right? But I think it would be a good idea to break that down, and we're going to be talking about that, the hypothesis test, using this new model, but in our next video. Okay, so that's it for now. Please take care and keep working hard. See you next time. Bye.